Hi, my name is Patricia Blanco Garcia. I am a principal scientist in the formulations team at Johnson Matthey's Technology Center near Reading in the south of England. I'm a chemist by training, and I've been using JAMP for about 4 or 5 years. And in this contribution, I'm going to talk about the role of data analysis in new process analysis technologies. If you haven't heard of Johnson Matthey, JM is a global leader in sustainable technology solutions, which are helping leading energy, chemicals, and automotive companies to decarbonize, reduce harmful emissions, and improve their sustainability. As an example, one in 3 cars are fitted with a catalyst converter from Johnson Matthey. And in November 2023, JM enabled the world's first commercial transatlantic flight powered entirely by sustainable aviation fuel. Most of Johnson Matthey's products are formulated, and this picture illustrates that. So from the left, we have catalytic converters that go in the exhaust of cars, and these are coated with a slurry that contains the active catalyst. The second picture is a fuel cell ink, and these inks are deposited to produce coated layers for fuel cell and electrolyzer applications. And then we have powders that they are using in inks, but they are also used to make granulated or pelletized catalysts that they are used in the production of chemicals. So the formulations contain a mixture of dispersed particles and also polymers and additives in a solvent. And as I mentioned, one example is the autocatalysts that go into the emission control systems. So in this case, the active materials for the autocatalysts are dispersed onto mixed metal oxide powders, and these are formulated into a slurry. And that slurry is then coated onto the supports that go into the exhaust of the car. And at JM, we produce hundreds of kilos of batches of these slurries, and they are milled to certain specifications. So for us, addressing the processing step of these materials is crucial to sustainability, both from the point of view of the use of materials and also the use of energy. And therefore, introducing online measurements is very important to achieve this. So the team I work in was part of a Horizon 2020 project, which was developing real-time laser diffraction technology for particle size analysis during the processing of inorganic catalyst dispersions. So particle size analysis is a critical measurement for many of JM's products and is part of a characterization suite for defining the pass-fail criteria for products in different businesses. However, particle size measurements are not online. So ideally, you want a measurement here, but in our case, the samples are mostly collected manually at unspecified time scales, and then they're measured in the lab. So the samples can age, and they can also be measured by different operators, and this is inefficient, and it can lead to repeatability and reproducibility errors. And therefore, real-time measurements are important because they allow accurate endpoint assessment of expensive milling processes, and they also minimize the risk of overprocessing. So what I want to discuss in this poster is the use of different control charting approaches for complex in-process measurements such as curves and distributions, and how the use of statistical tools together with automation and data management are critical towards efficient and sustainable manufacturing processes. So whilst in R&D, there is greater emphasis on extracting numerous complex measurements to characterize products. In manufacturing, the pass-fail criteria tends to be based on a reduced number of metrics and is often based on a single value data. So for example, percentiles of a size distribution like shown here on the right. But a complex particle size distribution is better described using the full curve, like the ones on the left. On the left-hand side, the different colors correspond to different intervals in the milling time. And in both cases, we are showing a comparison between online and offline data. And we can see that the trends are comparable, but it's all very subjective. So the use of statistical tools can help us to be less subjective. So the first tool that I want to show you is the control chart. And control charts are specifically used for online monitoring of one or several process variables. And these process variables can be temperature, pressure, etc. And the x-axis will be the time. So in this example, we are looking at particle size measurements for a powder sample, and we are monitoring the percentiles independently. So we have the D10, D50, and D90. And the percentiles, although we use them all the time, they're not very good descriptors for a multimodal distribution. And therefore, the ultimate aim is to monitor or visualize the whole curve, not just the percentiles. So we can build curve control charts to help us visualize a whole distribution, not just a value. And this methodology we adapted from Nicola Brammer from Solvay, who presented this at last year's summit. And she uses this tool to monitor a batch process, but we have adapted it to monitor particle size measurements. So the individual control charts are constructed for each size class in order to be able to build the curve control chart. And the control limits are a representation of the inherent variation in the process. So we use historical measurements to calculate the control limits based on previous measurements. So visually, we can see if the process is out of control, if a curve is out of the control limits. So the green line shows a current measurement plotted against the mean of the measurements, which is the solid black line, and against the upper and lower control limits, which are the dotted lines. And I mean, as well as control limits, we could also add spec limits if we wanted to. This is arguably better than the previous control chart because here we're looking at the whole distribution, not just a set of values, but it's still just visual. So if we take this one step further and use principal components, we can monitor the size distributions, the principal components of each curve. So in this case, the principal component analysis model-driven control chart allows to monitor the distribution using functional principal components for each of the curves. And a control chart can be created to represent the whole distribution, which is based on the functional principal components. So I hope I have shown you that real-time measurements of process parameters are critical to control processes, and that statistical tools can help to extract the most value of the data we produce. So we are working to deploy this approach to real case studies, both in R&D and in manufacturing settings. And to conclude, I'd just like to thank George Platt and Chan Malde from supplying some of the milling data in this presentation, and also Pilar Gomez for all her help turning my ideas into tools that we can apply to our data. And thank you for listening.